Okay, welcome back. We're going through pages 3 and 4 in your acid, base, and pH POGIL. So we're finishing up with the previous page of naming bases. So we're going to see what would the name be for the base with the following formula, BaOH2. Now this 2 just lets us know that Ba is in group number 2 on the periodic table, just like calcium over here, but it doesn't affect its name. So naming bases is very easy. You name your metal in front, so Ba would be barium, and then for these strong bases, they all have the same anion of hydroxide. So we'll see that this is a base because of that OH group there. So now let's look at some naming acids. What makes an acid unique and how are acids named? So there are all different kinds of acids. There's acids in food, industry, and research. And it's all about how they covalently bond with these other molecules and produce different ions. Their signature ion is H in front. Now, we can also see that water will form these hydronium ions, but we won't focus on that yet, not until we get to pH. So, we looked at the different properties of these substances, and now we're going to look at how they name them depending on what they're with. Now, this is a chart of binary acids. So, we'll see our binary acids have an H in front and then has an anion on the back end. So, an H in front and an anion on the back end. H in front, anion on the back end, H in front, anion on the back end. Now, if we look at their names, they're all very similar. We have hydro, 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 hydro. We have an ending of ic, 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 and ic, and then we always add acid to it. So that becomes important when we're looking at the formulas. So what prefix is used at the beginning of all of these binary acids? So prefix comes in front. We're going to see that the prefix is hydro. Now, what suffix is used at the end of each of these? So we're going to see that the suffix is going to be ic. Now, the prefix bi means two. Propose a reason that the acids in Model 1 are all referred to as binary acids. So if we take a look, we would see our first element is hydrogen and our second is that. We have our first as hydrogen, our second is Br. Our first is hydrogen, our S is our second, H is first, fluorine is second. Now there's only a 2 here because this one's diprotic, letting us know that sulfur is in group 16 on the right side of the periodic table. So how many wheels does a bicycle have? It has 2. So propose a reason why these are all named binary is because they have 2 elements. The first one has to be H, and then we'll have some other nonmetal at the other side of it. Now, fill in the blanks for naming binary acids below. If you have a hydrogen and a nonmetal, add hydro to the front, change the ending to ic, and don't forget to add acid as its last name. So if we have our binary of HCl, we'll see it's hydrochloric acid. If we have HBr, it's hydrobromic acid. So we'll still use those root words that we learned earlier in our lessons. Now remember that sulfur and phosphor are special. They have a little bit more to the root than the other ones do. Model number 2 is now ternary acids are known as oxyacids. So we're going to look at the formulas. Our formulas are here and our formulas are here. How are ternary acids different from binary in their structure? So binary, there were only 2. You had H and an X. We'll see that ternary has 3 elements, meaning you're going to have an H, some nonmetal, and then you have an O. So that's why they're known as oxyacids, because they contain oxygen. Now, what do you think the prefix ter mean? Now, if you are in your art class, you'll learn about your ternary colors. You have your primary, you have your secondary, and then you have your ternary, meaning that it refers to you having 3 colors mixed together. So, flip over to page number 4. We still have our model of ternary acids and oxyacids. Examine the pairs of ternary acids in Model 2 that contain sulfur, phosphorus, and nitrogen. Each pair has one that ends in an IC, and one that ends in an IOS or OUS. Complete the statement below with the correct acid naming. So if our polyatomic anion ends in 8, the acid naming ending is what? So I'm going to highlight it out to help us see what we're focusing in on. It said to focus in on sulfur. It said to focus in on phosphorus. And it said to focus in on our nitrogen one. So you'll notice when we're focusing in on it, we have 8, and then we have 8, and then we have 8. So our 8s go to what? Our 8s go to ick. So if you ate too much, you feel sick, so ick. And then if we look at the reverse, we see our ending ends in ite. What happens to our acid naming? So we have ite to us, we have ite to us, and ite to us. Now this one got a little messed up. We see it's ClO, you'll have tiny 2 and negative 1 there. So if we have chlorus acid, we know it ends in us, so we go back to our naming. We're going to see that chlorite became us, and then the charge lets us know how many H's we need. So we'll only need 1. So we're going to have HClO2. Okay, that's similar to its counterpart of chloric acid, but it's just 1 O short compared to chlorate because this is chlorite. Now, circle the acids below that would be named beginning with the prefix hydro. How did you choose those ones? So keep in mind, if you have a hydro prefix, they have to be binary. So keep in mind, binary means 2, H and an X. If it has O, it's not binary. HF, that would work. H2S works because it's 1 element, 2 element. There's an O, it doesn't work, and there's an O, it doesn't work. Now the final section on this page is the self-ionization of water. Since acids and bases react with one another, we'll see that they can actually react with itself. Water molecules can actually exchange their protons. So we can see that we can have H plus OH minus to give us water. And we use this because remember earlier in our lesson, it's amphoteric. So we're going to have our first formula here. We have our Kw. It's a constant for water. So remember, constants can't change. So it's always going to be 1.00 times 10 to the negative 14 molarity squared. And we can actually find that by taking the H plus times whatever the O minus is for it. So you at least need the H plus or the OH minus because our constant never changes. So what is the H plus concentration if the OH minus concentration is 1.0 times 10 to the negative second molarity? Now this problem is already done in your packet for you. So we're going to use our Kw equation, which just says we're going to take the concentration of H plus times OH minus. We know that Kw doesn't change, it's a constant, so I'm going to write that out first. Now it says, what is the H plus? So that's my X, and I'm going to have my 1.0 times 10 to the negative second M here. So like we've been solving before, how do we get X by itself? We're going to divide both sides by that OH. So that side cancels out. Now, in math class, when you have exponents and you're dividing, you're actually going to subtract. So what's 1 divided by 1? 1, excellent, times 10, and then what's a negative 14 minus 2? 2 negatives make a positive, so we'll see it's to the negative 12, and then one of our m's cancels out. So we'll see that the H plus concentration would be equal to 1.0 times 10 to the negative 12. So if we take a look at a number line, and we had our OH at negative 2, and we had our H plus all the way at negative 12, we would see that our OH had the greater concentration, so this one would be more basic because it's closer to 0. So what's the rest of the formula for our Kw formula? We take the concentration of H plus and we times it by our OH minus. When H plus and O minus are equal, you're going to have a neutral solution. When H plus is greater than, it's going to be an acid or acidic. It's because that's its signature ion. When H plus is less than it, you're going to have it be basic, because we'll see that the OH minus is its signature ion for it. So when you're doing these KW problems, you might want to pause the video and then come back and check your work for it. So if H plus is 1.00 times 10 to the negative fifth molar, what is OH minus? Is it neutral, acidic, or basic? So our Kw is equal to our 1.00 times 10 to the negative 14 molarity squared. We have our H plus is 1.0 times 10 to the negative fifth m, and we don't know our OH. So I'm going to divide both sides by that 1.0 times 10 to the negative fifth. I'm going to divide this side by the 1.0 times 10 to the negative fifth, and we'll see that what's 1 divided by 1? It's 1 times 10, what's negative 14 minus 5? So we're going to see what's negative 14 plus 5. We'll get a negative 9 for it, and then one of our molarities cancels out. So if we take a look at this problem using our number line, we'll see that at negative 1, 2, 3, 4, 5, we have our H plus. All the way at negative 9, we have our OH. So we would say our H is bigger, so this solution would be acidic for it. Okay, example number 2. Calculate the H plus concentration if the OH is now 3.0 times 10 to the negative second molar. So our Kw is equal to 1.00 times 10 to the negative 14 m squared. I don't know my H plus, so that's going to be my x. And then I'm going to have my 3.0 times 10 to the negative second m. So to get it by itself, we're going to divide both sides by 3.0 times 10 to the negative second m. And I'm going to divide this side too. So for this one, it's a little bit trickier mental math, so you might want to pull out your calculator for it. So let's do it first. What's 1 divided by 3? We get our repeating 3. So we'll round it to 2 sig figs for this one, so 0.33, and then times 10 to the, remember we're going to subtract. What's negative 14 minus 2? So we'll add it to the negative 12th m. Now we can put in proper scientific notation like 3.3 times 10 to the negative 11, or you can just leave it as is. It doesn't matter to me for it. So you've now finished pages 3 and 4. Thanks for watching.